Welcome back, everybody. I spent Monday telling you about anisotropic Gaussians, or to put it another way, the standard multivariate normal distribution, and trying to give you some intuition about the contours and the ellipsoids that you get out of that method. Having established that foundation, I want to come back today to Gaussian discriminant analysis, which I taught you last Wednesday, and today we're going to do it again. It's just now we're going to do it with these more general anisotropic multivariate normal distributions and see what changes. And to some degree, the answer is not much changes, but the plots look more cool. So recall from last lecture the PDF of the Gaussian distribution, or the multivariate normal distribution, to give it its proper name. So it is, I like to write it composed of two functions, remembering that the first function, which we'll call n, is a function that maps a scalar to another scalar. And again, it's monotonically decreasing function. And the second function, the q function, is purely quadratic in x. So this one takes a vector and maps it down to a scalar. So again, n is a function that maps a real number to another real number and includes an exponential and some important constants. This sign here, the bars around sigma, are the determinant of the matrix sigma, which is the covariance matrix of the distribution. And the function q takes a vector in feature space and maps it down to a single real number. And this one is quadratic, so it's relatively easy for us to understand. All right, so the covariance matrix, again, appears in two different places, here and here. And the covariance matrix plays, a crucial role in our intuition about the multivariate normal distribution. And its square root also plays an important role. So let's go through that. First of all, let's consider sigma. And let's write out its eigendecomposition. I'm going to write it as V capital gamma V transpose. This is, of course, the covariance matrix. And if I eigendecompose it like this, then remember the thing in the middle is a diagonal matrix. I've named it gamma instead of lambda because I'm going to have lambda be something slightly different. But this is a diagonal matrix that has the eigenvalues of sigma because it's an eigendecomposition of sigma. And those eigenvalues, we can think of them as being variances. Now, when I say variances, remember the univariate normal distribution has a variance term called sigma squared. So these are the sigma squareds, basically, are those eigenvalues on the diagonal of this matrix. And so each variance is associated with some eigenvector direction, a vector in V. And we can actually write out these diagonal elements and think of them as being a sigma squared, but there's a different sigma squared associated with each eigenvector. So those are all variances. When you are thinking about what the actual Gaussian looks like, it's more intuitive to think about little sigma than sigma squared, because the width of a univariate Gaussian is proportional to the standard deviation, which is the square root of the variance. So that's just little sigma. So it is actually quite useful for us to think not only about the covariance matrix, but the square root of the covariance matrix. Which, recall, since sigma is a symmetric matrix, always, we can just eigendecompose it, take the square roots of all the eigenvalues. Also, sigma is also always positive definite in this distribution, and therefore all of its eigenvalues are positive and have square roots. And this function is the one that maps spheres to ellipsoids. So if you want to imagine what the ellipsoidal isocontours of the normal distribution are going to be, what you do is you start with some spheres and you map them to ellipsoids by multiplying them by the widths of the Gaussians along each dimension. So now, this sigma to the 1/2 essentially corresponds to what was A in the last lecture. And so these eigenvalues are the eigenvalues that were in capital lambda last lecture. These are the eigenvalues of sigma to the 1/2. And you can think of these as the widths of the Gaussians. Or you can think of them as the radii of the ellipsoidal isocontours along each of the eigenvector directions. But, of course, they're also just known as the standard deviations. So the square roots of the eigenvalues of the covariance matrix are just the sigma i's, our standard deviations. And so, visually the way we interpret that is you just imagine you've got a simple function z squared on the left whose isocontours are spheres, and you take each of those isocontours and you apply the square root of the covariance matrix to those points. So, for instance, if you look at this point on the innermost isocontour, then if you map that vector through sigma to the 1/2, you're going to get this vector. And that is one of the eigenvectors of sigma to the 1/2. So if we look at the corresponding eigenvalue, that tells you how much longer that vector gets. And of course, so you can think of that as maybe sigma 1, and then there's another eigenvector in this direction. You can think of that, here it's the minor axis of this ellipse, so that's sigma 2. And just a reminder that this is the quadratic form, not of sigma, but of the inverse of sigma. So the inverse of sigma obviously plays a really interesting role here, and that, in a sense, it can also be interpreted as a metric tensor, which is part of the reason why it has its own name. It's sometimes called the precision matrix. By the way, if you don't know what a metric tensor is, don't worry about it, but if you've seen that kind of math, maybe this is helpful a bit. And what it does here is it defines the isocontours of our Gaussian. And let's recall again how that happens. This is the same thing I showed you last lecture. So just to quickly review, on the left, we've got a quadratic function, this q of x, and then we run it through this scalar function n of x, which again is a monotonic decreasing function, nothing very complicated going on. And we wind up with, well, here's what the Gaussian PDF looks like. And so every isocontour of the quadratic function is an isocontour of the Gaussian PDF, but with a different iso value. And because the function in the middle is monotonically decreasing, that means that the minimum of the quadratic function, which is 0, is going to become the maximum of the Gaussian function. And that's at the point mu. All right, any questions about this review? All right, so now what we want to do is we want to use these ideas to develop Gaussian discriminant analysis like we did last Wednesday, only this time we're using a more general form of the normal distribution. So the first thing we need to look at is how do we change the maximum likelihood estimation when you are now doing more than one standard deviation or different standard deviations in different directions. Well, I assume that you're given some sample points, x1 through xn, and class labels, y1 through yn, and you want to find the best fit normal distribution for each of those classes. And just a reminder that we are going to interpret xi as a column vector for the purposes of the math that's about to come. All right, so last Wednesday for the isotropic case, I actually went through and derived the answer for you. I'm not going to do that again this time. I'm just going to tell you the answer. For QDA, if you go through the derivation, then you will get the following approximation to the covariance matrix for class C by taking all the sample points that are in class C and doing the following computation with them. All right, and this thing is called the conditional covariance matrix. For the points that are in class C. Now, the word conditional, it means class conditional. It means conditioned on this point, these points being in class C. Let's look at some of the details of the conditional covariance matrix. First of all, mu hat C, well, that's just the mean of all the points in class C. This gives us our sample mean for class C. The product of xi minus mu c with itself, this is not an inner product again, this is an outer product. So this is going to give us a rank 1 matrix, and it'll be a d by d matrix. This sum here, this is summing just over all the points in class C, omitting the points in the other classes. And lastly, NC is the number of points in class C. So when you look at the sum and then divide by NC, that means we're just taking an average. We're taking the average of all these outer product matrices, one for each sample point in class C. And of course, although each individual outer product matrix has only rank 1, when you add a bunch of those matrices together, you could get any rank, or at least rank NC. So in order to do Gaussian discriminant analysis, you need to know how to compute this for QDA. And you also need two other things, but we're going to compute them exactly the same way we did last Wednesday. So we need the prior probability that some random sample point is in class C. Just like last week, we estimate that by taking the total number of training points in class C and dividing that by the total number of training points, period, in all classes. We also need to estimate the mean, mu, for points in class C. And once again, that's just the average of all the points in class C, just like it was last Wednesday. The only thing that's changing is that the way we compute the covariance matrix is different because now it's a matrix and not just a scalar. So here's a handy illustration of what it might look like if you actually do that. Here somebody has taken some sample points and run it through this equation here, and the output, they have graphed its quadratic form. Well, that's probably the quadratic form of sigma inverse, but whatever. And so you can see how our Gaussian comes out being fit to the points. So again, this is a Gaussian generated from points, not points generated from a Gaussian. And that's what you got to do in practice if someone gives you data. Now, one thing to note here is, as I think you all have been exposed to the proof of this by now, that this sample covariance matrix is always positive semi-definite. It's a sum of positive semi-definite matrices, so it has to be. But it's not always definite. It is possible that you have a singular sample covariance matrix, and the normal distribution, recall this PDF up here, this is not defined if you have a singular covariance matrix, because remember right here we have the determinant of the covariance matrix. And if that's 0, then you're dividing by 0. There are ways you can massage your way around that sometimes, but in practice you need a non-singular covariance matrix. Is there a question? Do you what? So yeah, one way to treat this would be to simply restrict your PDF to some subspace of the overall space. But that tends not to work really well with real data, because then if you get test data that's outside of that subspace, what do? So I don't want to say too much about what you do because I think that's a question on homework 3. But anyway, this is a problem. Again, in homework 3, there's a question where we ask you to think of a creative way to deal with a case where this turns out to be singular. All right, so at this point, that's everything you need to know to do QDA. After this point, you just apply Bayes' theorem as usual and get an answer, which I'll show you an example in a minute. But first, let's see, how does this change if I want to do linear discriminant analysis? So remember, with LDA, we are assuming that every class should have the same covariance matrix. So we just compute one covariance matrix for all the sample points, sort of. But it's not the standard covariance matrix for all the sample points. It is what's called a pooled within class covariance matrix. And that is an important distinction. All right, what does that mean? Let's focus on the within class part of that. Within class is referring to the fact that when we do this part of the computation for a particular sample point, we are doing it with the mean of that sample point's class. We're not doing it with the global mean. We're doing a separate mean for each class. And so one result of that is, suppose that one of your classes has contours like this, one of your classes has contours like this. Well, we're forcing them both to have the same covariance matrix, which is why they're tilted in the same direction, but we're not forcing them to have the same mean. The one on the right, this is mu for class D, and the one on the left, here's mu for class C. And if you compute the covariance matrix in this way, you might get that. Whereas what would happen is if you didn't do within class? What would happen if you just computed one sample covariance matrix for the whole input set, for the whole training set? Maybe you'd get something more like this. More spread out, usually, because different classes are in different places. So the black contour, again, that represents the sample covariance matrix for all points, and that's not what we want. We want these contours defined by the blue points and the red points separately. Then what we're going to do is, you can see there's sort of a double summation here. The outer summation is summing over all the classes, and then within each class we are summing the individual contributions from each sample point in that class. And then we divide by the total number of sample points. So when you put those three things together, we are taking an average of a bunch of rank 1 outer product matrices. And it's just that each of those outer product matrices may be computed off of a different mean. Any questions about that? All right, well, let's take a look at what QDA looks like when we do this. So remember, the way that QDA works is that we are choosing the class C amongst however many classes we have that maximizes this thing, which almost looks like the posterior probability, but we've thrown away the denominator because that's going to be the same for every class. And I'll note here that if you want, you can optionally add a loss function. If you have an asymmetrical loss, you'll need that. But I'm going to leave that out as I go through the rest of this procedure. The loss is handled exactly the same way as the prior is handled. And then, if I assume that what I want to do is maximize the posterior probability, because say I'm using 0, 1 loss, then that is equivalent to maximizing something called the quadratic discriminant function. You saw a quadratic discriminant function last Wednesday, of course, but now we're changing it a little bit. So, all right, here I'm defining it exactly as I did last Wednesday. The only thing that's different is that this PDF here is now the more general, not necessarily isotropic form of the multivariate normal distribution. And when we substitute that in there, therefore we're going to get something a little different than we got last Wednesday, because the quadratic term has changed. So that's our new quadratic discriminant function. And obviously, because we've gone from a scalar variance to a covariance matrix, this part has changed since last Wednesday, but it's still pretty familiar. All right, so this works for any number of classes. If I have 10 classes, if I'm classifying MNIST and I have 10 digits, then I have 10 quadratic discriminant functions, one for each digit, and I compute every one of them for any test point x, and whichever one is biggest, that's how I classify test point x. I can say some more things about this in the special case where we have just 2 classes. It would be nice to ask, where is the decision boundary between 2 classes? Well, obviously, the decision function, if you have a class C and a class D, the decision function is going to be QC minus QD, which is quadratic, because QC and QD are quadratic, but not necessarily positive semi-definite. It could be indefinite. And so what that means is that the Bayes decision boundary is a quadric. Reminder that quadric is just a fancy name for the solution of a quadratic equation in arbitrary dimensional space. If it's 2-dimensional space, it's a conic section. Also, we can figure out the posterior probability. So again, often you want to ask not only the question, what class is this test point? You also want to ask, what is the probability that this test point is in the class you just predicted? So if you want to ask that question, the answer is this posterior probability, which you can get just by applying the logistic to QC minus QD, like we did last Wednesday. All right, but now, because we're using anisotropic Gaussians, when you do this, you sometimes get things that are more interesting, a little bit weird in how they can appear. Here is an example where start with looking at this graph on the upper left, and the contours at lower left are the same function. Two different ways of visualizing the same function on the left. And that function that we're visualizing there, well, we're visualizing two functions. Let's say the blue curve is class C and the red curve is class D. And for each one of them, we have used through QDA, we estimated a class conditional covariance matrix for each of those two classes. And now when we plot the Gaussians that those give us, well, this is kind of interesting because it intersects in a funny way. You know, you see that the intersection line is a very interesting curve. It's actually a hyperbola. And if you look at the contour plot down below, you can see very clearly that is the decision boundary, that hyperbola there. Now, when we're actually computing this, we don't usually want to work with exponentials. We don't want to have to compute exponentials for every test point. So it is more natural, or more efficient, I should say, to just work with QC minus QD, because there we've taken out the exponentials. And so this is a quadratic function. And again, the figure at the top and the figure at the bottom are both the same function. So just two different ways of visualizing this quadratic function. The function itself is a hyperboloid. The contours that you get in the bottom are hyperbolae in 2D. So in particular, you can see the decision boundary here, because that is the contour with iso value 0. So QC minus QD is 0 on those two contours. And of course, I mean, part of what makes this example seem a little weird is the fact that the red region here isn't even connected. So there's red region there, there's red region there, but they don't have to be connected to each other. So then, if you also want to know the posterior probability, the probability that your prediction is correct, well, we take QC minus QD and we run it through the standard logistic function. And what comes out is our probabilities, numbers between 0 and 1. And once again, these two figures are the same function, just two different ways of viewing that function. And you can see kind of clearly that this function is bounded between 0 and 1, you know. It's either, the probability is usually really low or really high, close to 0 or close to 1, except in sort of this nether region here, where it's a little more ambiguous. And again, you can see the decision boundary in this contour plot because it is the set of points where the posterior probability is 0.5. Oh, I should... I forgot to write. This is the function that we're viewing. It's the posterior applied to QC minus QD. So when that posterior is 0.5, that's the decision boundary. Any questions about this? All right, well, you might wonder what happens when we have more than 2 classes, and then you can get a diagram that looks something like this. So this is basically an anisotropic Voronoi diagram, and this is what will happen if you have many different classes. Moving on to LDA. LDA, of course, is like QDA, except that we just have one covariance matrix that's the same for all the classes. And that, of course, is the pooled within class covariance matrix, is the one that we're going to use. Just like last Wednesday, the advantage of LDA is that the quadratic terms just cancel out, and you get a linear decision function. So let's see what that decision function looks like. If I'm comparing 2 classes, QC minus QD, well, take my word for it, they both have the same quadratic terms, so the quadratic terms are gone. And what's left over will be a linear term that looks like this. And you could call this a constant term, or you could call it several constant terms. All right, so I know that there's a bunch of stuff going on in this equation, but if you just look at the dependence on x, it boils down to here's a term that's linear in x, and here's a term that's just adding a constant. So this is in the standard form that we've been using for linear classifiers all semester, where our decision function is w transpose x plus alpha. Now, once you've seen this expression, you can bring it back to the case where you have many different classes. What if I've got 10 or 100 classes and I want to choose the best one? Well, you choose the class that maximizes something called the linear discriminant function. Which is mu c transpose sigma to the minus 1 times x minus 1/2 mu c transpose sigma to the minus 1 mu c plus the natural logarithm of pi c. Why does that work? Well, suppose that you're comparing 2 different classes, class C and class D. So you compute this expression at the bottom for class C, you compute a similar expression for class D, and then you compare them. Well, it's essentially what you're doing is computing the sign of QC minus QD when you compare them, because you'll notice that this term comes from here, and this term comes from here, and this term comes from here. And then if you compute the same three terms for class D, they're going to be different because mu D is different and pi D might be different. So that term for class D gives you that. That term for class D gives you that. This term for class D gives you that. So you can see that comparing these two linear discriminant functions for class C and class D is equivalent to computing the sign of QC minus QD. But the advantage of the bottom way of expressing it is now if I have 10 classes or 100 classes, well, I just compute one of these linear discriminant functions for each of the 100 classes, and then I pick the maximum one. And I can do that in order 100 time, not in order 100 squared time. If I had to compare every pair of classes, if I had to do this 100 choose 2 times, that would be more expensive. All right, so that thing works for any number of classes, but sometimes, again, we want to drill down on 2 of those classes to ask what is the shape of their decision boundary and what is their posterior probability. So if you've got just 2 classes, then the decision boundary, of course, is the linear, essentially the solution that sets this equal to 0. That's your decision boundary. So this is looking very much like a standard linear classifier. But one nice thing about it, though, is that you also can compute a pretty good estimate of the posterior probability, which is not something you could do with, say, an SVM. And again, you just take the decision function, W transpose x plus alpha, and you plug it into the logistic function. By the way, there's one tiny note that I want to make, which is that in this linear discriminant function, there is one rather expensive computation, which is here, computing sigma inverse times mu c, essentially, is what you're doing. That is solving a system of linear equations. But you only have to do it once. You have to do it, but you only have to do it once for each class. And note that exactly the same expression is there. So you don't have to compute it twice, just compute it once. That's going to be the most expensive part of this computation. And so do that once and reuse the result over and over again. All right, so now let's go look at what this looks like when we actually do it. So here again is an example where on the left we have 2 different ways of visualizing the 2 functions, fc and fd, the PDFs of our 2 Gaussians. One thing I want to note is that Mathematica kind of screwed up this plot, so over on the left where you see red, that's supposed to be blue. It's just the functions the plot didn't come out very well. But I think what's interesting, if you look at the decision boundary, well, the decision boundary is, as I promised, linear. It's a straight line. And, you know, the way that these 2 Gaussians are abutting up to each other, it looks like they're on an angle, they're jaggy, and yet you get a straight line. So that's kind of interesting, I think, that you can pop these next to each other like this, but you still get a straight line as your decision boundary. And again, the way we want to compute this in practice is not by applying an exponential to every sample point, but by comparing QC minus QD instead. And here you can see, as I promised, that now QC minus QD is a linear function rather than a quadratic one. And the decision boundary is, again, where QC minus QD equals 0. And just as with QDA, once you've got that, you can take QC minus QD, run it through the scalar logistic function, and what you get out are your posterior probabilities. And of course, the decision boundary corresponds to the line where the logistic function is exactly 50%. Any questions about that? Yeah. Are you asking if we have 3 classes? Okay. How do you deal with the training set versus the test set versus the validation set? Is that what you're asking? Yeah. Okay. So you only compute sigma C and mu C, the class conditional covariance matrix, and the mean for each class once from the training data. You will never change those numbers again. Once you've established your classifier, you have to keep using those same numbers. The test and validation data does not change what your values of mu C or sigma C are. Does that answer your question? Okay. It's a good question. So yeah, it's important to understand that once you've picked a classifier based on your training data, you're not going to change that classifier in response to the test points or the validation points. I found what I think is kind of an interesting application or instance of using LDA. This is just randomly found on the web, but what makes this a little interesting is not only is it a multi-class LDA, but if you look at the distribution of points in each color, they aren't really Gaussian distributed. They're I mean, if you look at each different color, they're kind of a mess. You know, the purple points, that doesn't really look like a Gaussian distribution. The green points, even less so to me. Nevertheless, even though they're not that close to Gaussian distributed, they're close enough that this probably gives you just as good results as any other method for these data. I mean, with this data set, it's hard to do really well, but this is what the LDA decision boundaries will look like if you use LDA on these points. Yeah? Does it make sense to use other distributions in some cases? Absolutely. If you know some distribution that you think is a better fit to your data than the normal distribution, you should absolutely use it. And the technique, the basic idea of decision theory and risk minimization, that works for any distributions. It may not be as easy to calculate because here I had this trick that allows me to reduce everything to a quadratic function. That's not going to be true for all distributions. But the general idea of applying risk minimization, you can use that with all kinds of different distributions besides the normal distribution. And you know, that's kind of one of the concepts I want you to absorb from this course, is that the way that we're doing risk minimization is very general and can be used, you know, for many different probability distributions. Is there another question? How do we know which distribution to pick? That's a very hard question, and somebody asked me that on ed discussion and I said, well, get a PhD in statistics. That's not completely a flip answer because it's a very open-ended question. It's almost a research question. And so you need to understand your particular application and try to use that understanding to figure out what kinds of distributions might be realistic to fit the data from your application. And there isn't an easy way to do that. Well, there isn't always an easy way to do that. Maybe sometimes there is. Mm-hmm. When you're trying to validate your model, what the loss function does is it essentially changes which isocontour we're going to use as as our decision boundary. So for instance, if you look at this again, then the practical outcome of using an asymmetric loss function is that maybe you will pick this isocontour instead of the black one. And that, once you've chosen that decision boundary, then when you get validation data, you're just going to use that decision boundary blindly, but it is a different decision boundary than you would have chosen for a symmetrical loss function. Does that? If you're talking about these plots here, these don't actually come from a data set at all. I just picked some parameters for the Gaussians. Yeah?
Going back to the asymmetric loss function, when we're writing our quadratic discriminant, you said we can put on a term for the loss function.
Mm-hmm.
What do we actually write in that loss function?
What do we actually write in the loss function? Is that your question? All right, so essentially, we are in the same place where we are multiplying by the prior, we can also multiply by a loss function. And assuming that there are only two classes, I don't even want to get into loss functions for more than two classes, because that can be more complicated. But if you have two functions, then this is either going to be L1 minus 1 or L minus 1, 1, depending on like one for one class, one for the other class. I'm not going to try to remember which one is which now. Once you've made that decision, then you can, that just becomes another logarithm here. And except for the other class, it's the reverse loss function. Does that answer your question? Okay. All right, so now that we know what LDA and QDA are, I want to sort of say a bunch of different things about them and how you can think about them, how they're used in practice, etc. So first of all, when I was looking at the statistics literature on this, I noticed that for some reason statisticians really like to interpret LDA as taking a bunch of points and projecting them onto essentially the normal vector. So think of the normal vector as being a line. Take all the points, project onto that line, and then cut the line in half at the decision boundary. And so this illustration shows what that looks like. It's not a very clear illustration, but this here is the decision boundary computed by LDA. And so the normal vector to that decision boundary, of course, will be pointing in this direction or the opposite direction. It doesn't really matter. What we really care about is the line that passes through W, the normal vector, or sorry, that is the extension of W, the normal vector. And now what this diagram is showing is that if you take each point and you project it onto that green line, then there is essentially the line is cut into two pieces right here, and everything on the bottom half of the line is going to be classified as a blue point. Everything on the top half of the line is going to be classified as a red point. Of course, that classification is not always correct, but that's what we're going to do. So this is just an equivalent way of viewing this, but maybe it's helpful for somebody to think about it that way. One thing I want you to think about is the number of parameters that these two methods are learning. And so we're going to stick to the case of just two classes. In the end, LDA learns D plus 1 parameters because it's just another learning method with a linear decision function. And so you can describe that decision function in terms of the normal vector W and the bias term alpha. And that's all. That LDA may do a lot of work to boil it down to just D plus 1 parameters, but in the end, there's only D plus 1 parameters left over. QDA, well, it has this quadratic term, and the quadratic term adds a quadratic number of parameters because you have all the cross terms. And so if you work it out, then it comes out to this many parameters. And again, the important point is not exactly how many that is, but the fact that it's order D squared if you have D features. So because of that, it is often found in practice that QDA is more likely to overfit your data. And the dimension is much bigger when the danger is much bigger when the dimension D is large. But on the flip side, LDA is more likely to underfit your data because it can only generate linear decision boundaries. And in your textbook, they give an example of this to kind of illustrate what can happen. In this figure here, the left example is LDA, and the right example is QDA. I'm sorry, no, that's not right. No, this is two different data sets, and each data set is showing both LDA and QDA. So my apologies. Two different data sets. Each of these were generated from synthetic data, so the authors know what the Bayes optimal decision boundary is, because they generated this data with a computer, and that's the dashed purple lines. So on the left, we're going to see an example where the Bayes optimal decision boundary is there, and it's a straight line. And on the right, we're going to see an example where the Bayes optimal decision boundary is actually curved. Now, if the Bayes optimal decision boundary is curved, obviously a linear classifier isn't going to be able to approximate that boundary very exactly. Now, in this particular case, well, actually, in both of the sides, this blacked dotted line is LDA. And the curved green lines are QDA, which can create a decision boundary that's not straight, unlike LDA. And it turns out that in the example on the left, LDA does better than QDA. And in the example on the right, QDA does better than LDA. They're better fit. It's just a better fit to the Bayes decision boundary. So when you're deciding whether LDA or QDA is better, one of the things that you would like to know is, what does the Bayes optimal decision boundary look like? You don't generally know that, but sometimes data can be well by a linear classifier, like on the left, and sometimes it can't, like on the right. And so in the latter case, QDA is probably more likely to succeed. In the former case, QDA is more likely to overfit your data. Any questions about that? Yeah. Yeah, QDA and LDA don't really have parameters to overfit or underfit. What you can do is you can try LDA and you can try QDA, and you can use validation to see which of the two is better. But I don't know of a more general knob for cranking up or down the underfitting or overfitting than that. There's probably ways to regularize QDA, but I've never actually seen that written down. Yeah. If you have enough data, can you calculate what? Oh, Bayes optimal. What I would say is that if the points really are normally distributed, if the actual process that generates the points is so close to a normal distribution that you can count on it, then in the limit, as the number of points goes to infinity, oh man. In the limit, as the number of points go to infinity, the estimates of the mean and the covariance matrix for each class will get closer, more and more accurate. And the decision boundary you get hopefully will converge to the Bayes optimal decision boundary in the limit as you go to infinity. So I want to remind you that with almost any learning method, you can always add new features. And so if you take a linear method and you add features, it's not a linear method anymore. So even LDA can give nonlinear boundaries if you add the right kinds of features to it. And whether that's good or bad depends on whether the features you add fit your application or not. And QDA can give boundaries that are not quadratic but are more complicated than quadratic. But I hasten to add that if you use LDA with quadratic features, although you'll get a quadratic decision boundary, it's not the same decision boundary that QDA would find. And another thing I want to point out, just relevant, very relevant to the last question I was asked, is the fact that although QDA and LDA are motivated by trying to find the Bayes optimal classifier, you don't actually get the exact true Bayes classifier for two reasons. The first is that we're estimating the distribution parameters, the mean and the covariance matrix, from a finite data set, and we don't usually get those numbers exactly right. And the second reason is because most real-world data sets are not actually perfectly Gaussian. So again, the Bayes optimal classifier is this idealized goal, like a platonic goal that we reach for but can never really attain. And while I don't want to go through the details of this, I do want to point out that when you change the priors of your classes, or when you change the loss function that you apply, essentially that can be interpreted as adding constants to the discriminant functions. And therefore, you're just moving the decision boundary to a different isocontour. So this is very easy to do. Since you're just adding a constant, you can do this post facto. You can train your classifier, and then you can change these constants at the last minute. And when we're looking at the posterior probability, of course, normally we pick the decision boundary with 50% probability, but we don't have to. We can pick the decision boundary for 10% probability, or 50%, or 90%, or whatever you want. And by doing so is equivalent to either changing your prior probabilities or using a different asymmetric loss function. So in particular, it is possible to show, why did it do that? It's possible to show that if you, instead of picking the 50% ISO value, you pick the ISO value equal to p, think of p as some probability, that is equivalent to choosing an asymmetrical loss where the loss is going to be p when you have a false positive and 1 minus p when you have a false negative. Or another way to interpret choosing the ISO value to be p instead of 0.5 is that it's equivalent to what we would have gotten if we chose the prior for class C to be 1 minus p and the prior for class D to be p. And the last thing I want to say is that LDA and QDA really are used in practice. It's not just a theoretical algorithm. It works great for some data. There was a project called StatLog that tried to evaluate many different learning algorithms on many different data sets. And they found that either ALDA or QDA were in the top 3 classifiers for 10 out of the 22 data sets they used in the project. And it's not necessarily because those data sets are Gaussian. LDA and QDA sometimes work even for data that's not that Gaussian, but does support simple decision boundaries, such as linear or quadratic. And the reason is that Gaussian models provide very stable estimates that aren't easily changed or disturbed by bad data. Any questions about any of that? Yeah.
Can QDA give a linear boundary?
Can QDA give a linear boundary? It can give you one by chance. If the quadratic term just happens to come out to be 0, then you get a linear boundary. That can happen. I mean, with real-world data, tiny random fluctuations will tend to make that come out slightly non-zero, the quadratic term, even if it's close to 0. So it doesn't happen very often in practice, but it could. So the last thing I want to do today is discuss some terms that are related to some of the stuff we've learned in the last couple of weeks, starting with, I don't remember if I specifically said this before, but the input matrix we get of points and features is often referred to as a design matrix. So the sample points come in a design matrix X, which is n by d, because every row is a sample point, and there are n of those. And every column is a feature. Now, we have kind of a clash of notation here, because up until this point in the lecture, I've been using capital X to denote a random variable, and now that's changing. Capital X is now a matrix. Sorry for the confusion, but this is kind of the standard notation that everyone uses. There are tons of machine learning papers where the design matrix is capital X. There are tons of probability statistics papers where the random variables are named X. So we're going to have a notation conflict here, and you just have to try to infer from context which one we're using. Also, I want to point out that in our matrix, each sample point is going to be a row of the matrix, but when we pull it out to use it separately, we usually want it to be a column vector, and that is why I'm writing xi transpose here. xi is the column vector that I care about, but xi transpose is the row of the matrix when it's still in the design matrix. So sometimes you'll hear someone talk about centering a data matrix. What does that mean? It means you compute the sample mean, or the mean for the class, as the case may be, and you subtract that from each row of the design matrix. And so what that does is it takes us from a matrix X to another matrix I'll call X dot. The dot means centered, and so the sample mean of the rows of X dot are 0. The effect of centering is to make the new mean be 0. Oh, and mu, of course, is a column vector that is the mean of all the rows in X. So again, the mean of all the rows of X dot are going to be 0. All right, so I'm going to define a probability distribution, which in one sense is very simple. It's just the uniform distribution. This is a discrete distribution on the sample points. Okay, one more time. R is a discrete uniform distribution. What it means is I'm taking a hat, I'm putting all the sample points into a hat, I'm stirring it well, I'm reaching into the hat and pulling out one sample point at random. That's what R is. When you take the covariance matrix of that distribution, R, then that gives us something that we call the sample covariance matrix. So using the definition of covariance matrix that I gave on Monday, if we we can work that out, and it comes out to this. Just x dot transpose times x dot, and then you divide by n to take an average. And I find this to be the simplest way to remember how to compute, for instance, a covariance matrix for QDA. Although, of course, with QDA, you want a class-specific covariance matrix. So, for instance, when you are computing the estimate of the covariance of C, then, of course, you're dividing by the number of points in class C, and you imagine that you have two centered design matrices that are only the points in class C. And so that gives us the covariance matrices that we need for QDA. All right, so centering is one step. Another step that sometimes people do with their data, when you have points that you know are from an anisotropic Gaussian distribution or something close to that, sometimes it's useful to perform a linear transformation that maps them to an axis-aligned distribution. And that is called decorrelating x dot. So decorrelating means that, well, if I compute the eigendecomposition of this thing, then I can use the matrix of eigenvectors to rotate x dot into a form where it's now axis aligned. So here's what that looks like. So first, you take the covariance matrix, the sample covariance matrix, and you compute an eigendecomposition of that, V times lambda times V transpose. And once you've got that matrix V, you can use it to rotate all of the points in your design matrix, which gives you a new design matrix, Z, where everything is beautifully axis aligned. Specifically, the variance of this rotated point set is going to be a diagonal matrix, the eigenvalues. So I think a picture helps to make this clear. So decorrelating, essentially, is going from the figure on the left to the figure in the middle. That's decorrelating. Well, there's two steps here, actually, which are centering the data and then rotating the data so that it's axis aligned. Sometimes you want to take a step further and you want to put your data into an isotropic normal distribution. So if you want to go from here to here, how does that work? Well, you can think of it as being in two steps. So when you have a centered design matrix, x dot, then sphering x is a word sometimes used to mean we apply the following transformation. We take our centered design matrix x dot and we multiply it by the square root of the covariance matrix of the sample points. And that gives us another design matrix, W, and the points in W look like this. And the term whitening is used as well, which is almost the same as sphering, except it includes centering first. So if you take some data and you center it and then you sphere it, that is whitening. So going straight from the original x rather than x dot to W. And if you do that, then The whitened sample points have a covariance matrix, which is the identity matrix.